Now I think we can start. Please, Roma.
Okay. Should I speak English?
I think yes.
Oh, okay, sure. All right. So today I'm gonna talk on a semi-infinite construction of twisted and actually like non-twisted also Fock module for quantum toroidal GL1. Let me start from a general introduction. Why do I like this algebra? Okay, so a famous construction says this algebra has remarkable representation like Fock module. Also, we can take tensor product of n Fock modules, and geometric representation theory says that this representation is naturally identified with K-theory of certain modular spaces of some sheaves on P2. Like here we took tensor product of n Focks, and here we take sheaves of rank n and sum of second Chern class. So this section, like this is one reason to like this algebra, because this geometric representation theory construction via certain correspondences.
D is the same thing as K, right, in this summation?
Oh, yeah, sorry. Yeah. Sure. Yeah, I decided to. Thank you. Then another remarkable feature of this representation is that like there's Q-deformed W algebra. It actually is a quotient of quantum toroidal GL1, and the action on this tensor product of Focks comes from action of W algebra. So this connects this story with CFT, because these W algebras appear in CFT as certain algebras of symmetries. But in this, like this, so this phenomenon leads to famous AGT correspondence. And I'm not the best person in the audience to talk about this, but like this is just a motivation. In this talk, actually, I would not consider tensor product of Fock modules. I will only take like one Fock module. Maybe I will make it twisted, but anyway, only one. And in case of one Fock module, as I said before, it can be interpreted as K-theory on certain modular space of sheaves, and in this case, this modular space are just Hilbert schemes of K points in C2. On the other hand, the space is identified with symmetric functions. In Fock module, there's like in this algebra, there's certain commutative subalgebra generated by operators P0B. I will explain the notation below. So this is commutative algebra. It has eigenbases, and this eigenbasis corresponds to McDonald basis in the space of symmetric functions and fixed points basis in the K-theory via localization. Yeah, it's a localized K-theory, of course. So like another bullet why people like why this algebra is connected to work of many people is connection with spherical double affine Hecke algebra. Quantum toroidal GL1 actually surjects to spherical Dhaka, and spherical Dhaka acts on space of polynomials in symmetric polynomials in n variables, and eigenbasis is the basis of Macdonald polynomials. In this case, it's not symmetric functions, but polynomials in n variables. So this was like famous features of this algebra, the like list for what people like this algebra. The list is not complete, which is just.
Sorry, what do you mean this is not, they're not symmetric functions? They're not symmetric functions of x1, xn?
They are like, I mean, oh, sorry, maybe it's like by term symmetric function, I meant like symmetric functions in infinitely many variables, which are not polynomials. And these are symmetric polynomials, and definitely they function in general mathematical sense. Yeah.
But lambda is a projective limit of lambda n, right?
Yeah, sure. Yeah. Thank you for your comment. Okay, and today I will explain certain construction about this on this quantum toroidal GL1. We will explicitly construct an action of this algebra on an integrable level 1 representation of quantum affine GLN. The quantum parameter V here is like Q2 to the power -1/2. So it's like expressed via these parameters. And so here I said that we will construct for GLN. The obtained representation will be isomorphic to twisted Fock module, twisted by an automorphism of the algebra. Like his group SL2Z actually is central extension of SL2Z, but let me not go to this deep. So there's some element from SL2Z. It's a matrix, and there's like 4 coefficients, and one of the coefficients is n. So this n appears here like quantum affine GLN, and I will construct action of quantum toroidal GL1 on this representation of a quantum affine GLN. Okay. Are there any questions about the introduction?
I'd like to say that this is some sort of duality, G1, GLN.
Yeah, sure. So like we have this Fi equals like identified with twisted Fock space, and on one hand there's action of quantum toroidal GL1, and on the other hand there's action of quantum affine GLN. Yeah, thank you. Okay, so the plan of today's talk is the following. First, I give a reminder on double affine Hecke algebra. Then I will give semi-infinite construction of non-twisted Fock space. Then we will consider the twisted case, maybe skipping some details because the things are analogous, but like a bit more tricky. Maybe we will have time for brief discussion of Gorsky-Negut conjecture, but I'm not sure about this, like if the time permits. Okay, so let me start from the reminder on Dhaka. So we've got like affine Hecke algebra. It is generated by elements T1, Tn, T1, T2, etc., Tn minus 1. And like this is a deformation of a symmetric group. So this oh my. So this algebra is the written relations are precisely the relations of the symmetric group, namely braid relation and like Ti, Tj, which are far from each other, commute. Also, there is like Hecke relation, which is deformation, the place where deformation actually appears. For v equals 1, this would be just the relation of symmetric group. So I wanted to use this coding like this. Green relations correspond to H. Then we consider affine Hecke algebra. I will underline it by red. It is generated by T1, Tn minus 1, and also by Y1, Yn. The relation are the following. So Y commute. Ti commute with Yj if j is not I and I plus 1. And also this relation Ti Yi Ti equals Yi plus 1. For v equals 1, this affine Hecke algebra is affine veil group. So it's just like smash product, semi-direct product of permutation group and commutative group generated by Y's. But like here we got the deformation, and now t square is not equal to 1. And here there's not like conjugation, but you've got Ti by Ti, not the conjugation. All right, and the whole double affine Hecke algebra generated by T's, Y's, and also one generator called pi. And the relations are the following. So if you conjugate of Yi by pi, then Y's are cyclically permutated. Here I mean that like Yn plus 1 is actually Y1. But like when you conjugate Yn, then also parameter Q appears. Yes, I didn't say it explicitly. The algebra depends on Q and V. V appears in the Hecke relation, and Q appears here when we conjugate Yn by pi. Also, when you conjugate Ti by pi, they are cyclically permutated. I did not include T0, so like I do not write this relation for I equals n, but you can define T0 as well. So it's just a matter of taste. I require that pi n Ti commute. So this is like the relations of Dhaka. Okay, like if you've got any questions at any point, please interrupt me, ask the questions, don't wait for the end of the talk.
Roma, it looks like from the last two relations that Ti plus n is Ti in some sense.
Yes, sure, yeah.
But then the question is, in the braid relation, let's see, if I put I equals to n, would I impose the additional constraint that Tn T1 Tn equals T T1 Tn T1 or not?
There is no Tn in my generators.
Right, but your formula looks like if I continue conjugating by pi. So in the last formula, okay, maybe the question is about relation pi ti pi inverse. Can I put I equals n minus 1 there or not?
Sure. In this
So it
way,
will be the definition of Tn, yes?
yes. You can
So-
define T0 or Tn like.
T0. Okay, so that would be T0.
It will be a new generator.
Yes.
It is not T1, T1.
Okay. Thank you.
Thank you. Any other questions? Okay. So the algebra has remarkable чередник basic representation denoted by Cu. It acts on Laurent polynomials and n variables. So we have generators yi, and they act just by multiplication by yi. There's such an abuse of notation, but you see what I mean. Okay, Ti acts by certain famous difference operator. Actually, this is induced representation. This representation can be interpreted as induced one, and you can actually get these formulas. You do not have to be чередник to write it, if you know that this is induced representation. Yeah, and also pi acts by like he's some constant u, representation depends on the constant, then qkn, and then I take just cyclic permutation of y's. So
Sorry, what is SI? I'm sorry.
oh, yes, thank you. SI is permutation of yi and yi plus 1.
So these are some kind of Dunkel operators?
Yeah, sure. Yeah, like you see what I mean. And so pi makes the cyclic permutation of y's. Oops, yep. With certain constant, so this u, and also we multiply by q to the k to the n.
I would say the Dunkel operators are not T and or pi are some x's. So
yeah.
So
Sure,
Dunkel
sure.
operators are different operators, and actual difference is inside P. So there are some products.
Yeah, thank you. This is yeah, maybe I'm not really good about the Dunkel terminology. Sorry. Okay, so what I meant to say, like, is that there's action another copy of affine Hecke algebra in this. I'm sorry, someone is not muted. Misha, please mute a person who is not muted. Okay.
Roma, and then this formula for xi's, who is xn? You have to start from T0 or what?
No. There's no T0.
Who is xn?
Xn is just
Pi minus 1?
Yeah. It's just pi minus 1 and then product of inverse t's.
But then in x1 you have
x1 is product of t's and then pi inverse.
okay, so okay.
Yeah, maybe the notation is a bit tricky for the, yeah. So this affine Hecke algebra generated by T's and this xi. It's another copy of affine Hecke algebra in Dhaka. And this is actually the reason why the algebra is called double affine, because it has y's and x's in the same algebra. And they like interchange in a very non-trivial way. One of the motivations why this algebra actually appeared in the work of Cherednik is that if you take symmetric polynomials of this xi and would act on symmetric polynomial in y's, actually, like here I write this like a subspace in the Cherednik representation. So action of these symmetric polynomials in X, it's a commutative algebra, and it actually has eigenbasis. And the eigenbasis is basis of Macdonald polynomials in Y. So, all right. Actually, I will not maybe literally use this theorem, but this is why Dhaka appeared. Okay, let me introduce spherical Dhaka. For a permutation W in permutation group, I consider minimal decomposition in product of SIs, the permutations, the transpositions of neighbor elements. And I denote by TW the product of TI1, TIJ. So for each element in the permutation group, I associate TW. Then I define V antisymmetrizer by the following formula. So I've got some not really important coefficient. So this is the symmetrizer, like just deformation of the usual formula. And this is antisymmetrizer. Okay. Now I can define spherical Dhaka. It is just usual Dhaka. Like I take all elements of the usual Dhaka multiplied by S on the left and on the right. So this is just subset in Dhaka. And it's this subset is closed under multiplication, hence it's subalgebra. It's non-unitary subalgebra, it does not contain one, but nevertheless it's subalgebra. So
Roma, the usual symmetrizers are projectors, I think, right? They square equals to themselves.
Yes,
Yes, plus and minus.
This one are also projectors. Sure. Okay. And this is important, like to have a unit, for example, in this algebra. You will need this property. Okay. So like one of the motivation to consider this spherical subalgebra is because it acts on symmetric polynomials, and like we can retell the previous story, like say that the corresponding, like you can take any polynomial in X, then take the corresponding spherical element of spherical algebra, and this will be Macdonald operators. So like the eigenbasis will be Macdonald polynomials. Okay, But my motivation.
Sorry, Rom, for trivial, or I missed something. You said that there is no unity somewhere.
No, it's non-unitary embedding. So like you've got one in this algebra, and you've got a unit in this algebra. It is like S plus minus 1. But but these are different elements. But both algebras has a unit. Okay. Okay, maybe I'm too honest, but let me introduce a central extension of SL2Z. I will denote it by SL2Z tilde. And this is, okay, I will say in an informal way. Imagine SL2Z, but now rotation by 2 pi is not identity. So you're like, it's like universal cover, but the group is discrete, but like rotation by 2 pi is an element of this Z, of this kernel. So this is central extension. The group is very close to just SL2Z. Let me not go into details. So this central extension acts on Dhaka. Actually, the honest SL2Z without central extension acts on spherical Dhaka, on both like spherical and anti-spherical plus minus. Moreover, this Dhaka has generators denoted PABN, and the action is just that element of SL2Z acts on PAB. You just apply SL2 element of SL2Z, this 2 by 2 matrix, to vector AB. That's the action, just standard action of SL2Z on Z2. Right. Then remarkably, we can write some of these elements, the most important, all the elements we need explicitly, namely P0K is, like here I write this like for certain constant. I don't care about the constant right now. So P0K is sum of y's to power k. PK0 is like, okay, here I put this symmetrizer or antisymmetrizer, then sum of x's. Then I will need P1b. It is actually here some algebraic computations involved, and by them we can have only one x. Here the formula is maybe a bit unexpected, but that's the formula. So we just wrote everything in terms of one, x1 and y1 to the b. Yeah, so I know what these generators are in terms of Dhaka. So let me show a picture for you. I know formulas. So this P1b was like first column, and he is like 1x, and like on the, if the coordinate is b, then there's y to b. Green column consists of these sums of yi to k. So here's some number of y and no x. Here in the blue column, we've got x inverse y to the b, and here we've got x's. So like to say it in mathematical way, the algebra is bigraded, and so the x, like the horizontal direction correspond to grading on x's, and vertical direction correspond to grading on y's. Okay.
Roma, why did you need to take the symmetric sums of powers of x and y for pk0 and p0k?
Actually,
take care of that automatically?
Actually, I just like formula in this way, because like it will give me Heisenberg at the end, like this green column will be Heisenberg at the end of the day. But you're right, in this case, you can put different constant. Oh no. It's just for k equals 1 works. Yeah, for general k, I think you cannot reduce.
I also think you cannot reduce.
You cannot reduce, yes. This simplification, which appeared for the red and blue columns, it appears because these vectors are primitive. They're not multiples of any integer vector.
I see.
Yeah, so for k equals 1, you can make the simplification, but generally not. Okay.
This formula could resemble the formula in definition of the Macdonald polynomial. They are eigenvectors of some symmetric functions. And this is more or less this function, the corresponding operators.
Yeah, but I just thought that S plus and the dressing with S is simultaneous automatically symmetrizes these functions. That was my impression, but maybe I was wrong.
It symmetrizes, but to different functions. The symmetric function, but not necessarily this power sum. I think, but I think so.
Well, it's a bit tricky. Okay, maybe I should proceed. So this, my favorite algebra quantum toroidal GL1 is generated by PAP and two central elements, C and C prime. This famous result by Schiffman and Vassero, which states that this a surjection from quantum toroidal GL1 to correspond to spherical affine Hecke, double affine Hecke algebra. Oh, I didn't write it, but what I mean to say is that PAB maps to the corresponding PABN introduced above. And here the parameters of quantum affine, so they are expressed via Q and V, and actually you take different Q2 whether you consider spherical and antispherical. Okay. So that's it about the reminder on double affine Hecke algebra. Now I want to proceed to semi-infinite construction if there are no questions. Okay, so now semi-infinite construction is about taking semi-infinite exterior power. Therefore, I will consider antispherical, like SH minus n. And like tautologically, it acts on, like using this Cherednik basic representation, I can obtain action of the algebra on S minus applied to the polynomials in Weiss. I would like to like I like the automorphisms that like it's a trivial thing that polynomials are in n variables a polynomial in one variable tensor in tensor power n. Just okay, let me to be very clear in this point and say that you take a monomial and map it to the corresponding tensor. Also, I will then, like as I said, when I apply S minus, this is okay. Actually, this is rather definition, but I guess I believe it gives some intuition. So this is V deformed exterior power, and I will use the following notation. So I take a monomial, apply antisymmetrizer, and the corresponding element is denoted as a wedge. Okay, so my idea is to take the limit n, capital N to infinity for these actions and obtain a representation of like all the, so repeat this surjection from quantum toroidal GL1 to this spherical Dhaka. And so quantum affine algebra acts on all these spaces. And therefore, like I have representations depending on n, and I'm going in certain sense, take the limit n to infinity. I will explain this below, but maybe before explaining the limit, I want to use certain algebraic calculations, namely my formula for P1b was this one, and I will use formula for x1, like as we discussed, it product of t's. Oh no, here's t n minus 1 pi inverse, yeah, and then y to the b. And so here I have product of t multiplied by antisymmetrizer. And this basic property of the antisymmetrizer, that when you multiply it by ti, it is the same as just minus v inverse s minus. Like this is just like ordinary symmetrizer for v equals 1, you know. And therefore, product of these t's actually give just a factor, and I get this formula. So now I've got y1 to b pi inverse dressed by s minus. And now I'm going to write a formula for this operator in terms of certain operators. Let me introduce the operators. So I consider a vector w in nth deformed exterior power. I also use this notation with tensors. What I mean is that exterior power is subspace is in tensor power. So like the V antisymmetric tensors there, and any element of exterior power can be written as sum of tensors, but not any sum of tensors belong to the exterior power. All right, and I will need two operators, maybe 4, but 2 for now on. First is just wedge with ek, it is denoted by psi k. And the second, so I recall the notation for w, w is this sum, and the result of action phi star is sum over j. here you see I use multi-index notation. So J is tuple J1, Jn. All right. And here I take only summands where k plus Jn equals 0. So Jn equals minus k. And then just put, okay, and just I write all the factors without the last one.
Both
Oh,
separators
no,
act
no, no,
on
no,
the
no,
right.
no, 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 no. You are right, Misha. You are right. Yes, I always confused right and left. I'm left-handed. This is some excuse. Okay. Yeah. So this is the definition of phi star. So it takes, yes, it takes the first. So if J1 is negative k, then we obtain the monomial, and if not, then we just forget about this monomial, like it maps to 0. Yeah. What is remarkable that like this element, one can check that it actually belongs to n minus 1 exterior power. And this belongs to n plus 1 exterior power. Okay. And I claim that pi 1b equals constant, and he is the sum q negative k psi k phi star. So what do I use here? Recall, like I want this formula to be clear to like everybody in the audience. So here I have this formula. Let's be inverse.
Sorry, Roma, J and J1 is the same?
J, where do you see? No, no, no.
Maybe you can write
No.
J равно. J
No, no, no,
equals
no.
to.
No, no, no. J is a tuple. Maybe I should write it like bold, but
You can
thank you.
underline or
Yeah,
overline,
I see.
like vector.
maybe I can make it bold.
Multiplication by ek, it's like the same as yk, right?
Oh, sorry. I didn't mean to use this notation as this part of the talk. Sorry.
But yeah, but it's more or less clear. It's not so
Yeah.
confusing.
Yeah, thank you, Andrei. Okay. Any other question? Okay, so what I want to say is that, okay, maybe it's too small, but before we had like two formulas. One formula is for P1B, it is like expressed via this y1 and pi inverse, and the second formula is for action of pi. So these symmetrizers I actually okay, the important, but maybe not, let's not look at them now. So what do we have? We have first we act by y1b multiply. So the first tensor multiple is like you add b to the index. Then you apply pi by the formula. So it's like you take this tensor factor from the left and put it on the right, right? This pi action. It takes a tensor multiple on the left and put it on the right. And this is exactly what the formula says. I apply first phi star and then apply psi k, psi, yeah. And if I just, but I'm not just tensoring, I'm wedging, therefore I need to apply the antisymmetrizer. Oh, that was a bit sloppy, but the formula is really easy. Are there anybody who wants to ask a question? Maybe someone wants to complain that the formula is not clear. I can explain it again. Kolya, is the formula clear?
Yeah, I just wanted to ask about n capital because on the one hand, in spherical Dhaka there is on one the thing is this generator capital, it preserves gradient, yes, by n capital. It preserves number of multipliers.
Sorry, which generator?
Yeah, the generator which you
superscript.
defined. Yes, yes. It can be determined uniformly for any n capital by the same formula. Yes, but it preserves n capital, so you don't need to.
Yeah. Sure. These operators, yes, they are maps from lambda n. Yeah. Thank you. This is actually a good point. So first I apply phi star, and this is map from nth power to n-1 power. And then I apply psi, and this is mapped from n-1 to nth power. And that's it. That's the formula. Are there any other questions?
For v equal 1, this is some fermionic type formula, yes?
Yes, sure.
This is not question, maybe comment.
Yeah.
Sign tester.
Mm-hmm.
So we have v equal 1, but q is still alive. So this inferment is like psi of z times psi star of qz.
Yeah, it's some sort of expanding the operator as sum of matrix unit. Okay, Andrei Grekov, is the formula clear? Do you understand?
Yes, I think.
Okay.
More or less.
Okay. If all the контрольные слушатели are happy, then we can proceed. So maybe I will introduce the current notation. So I'm introducing generator series for P1b denoted by EZ, and generator series for phi and psi are denoted by phi z and psi, okay, but for psi and phi are denoted by psi z and phi z, you see. Then the formula can be rewritten nicely as just product of psi qz phi z. Okay, let me say a few words on the limit, not going into many details. I've got a sequence of spaces like first, second, etc., exterior powers. And I've got the maps, which like vector here is mapped to vector wedge yn. You can impose some shift, but nevertheless, let me do this. And there's certain mathematical construction called inductive limit. Nikita asked about projective, not asked, commented about projective limit, but here for some reason I need inductive limit of the spaces. And the inductive limit is so-called semi-infinite construction. It contains like this semi-infinite wedges.
Projective limit is for symmetric functions, yes, usually. And here we have antisymmetric
Yes.
functions. Maybe this is the reason.
Yes, for symmetric functions, you can say that one of the variables is 0 and then get like less variables. And here we wedge.
So in this sense, it's a bit unusual.
Yes, at least in the combinatoric context. People in the combinatoric more prefer symmetric functions. Okay. Yeah, so this is the semi-infinite wedge formed actually. Okay, but actually this construction is very similar to just ordinary semi-infinite construction. In this case, like below we will consider twisted case, it will be harder. But here, these V antisymmetric functions are just symmetric functions times V Vandermonde polynomial. So everything is very simple. And moreover, the limit is identified with symmetric, it's basically it is identified with ordinary semi-infinite power, and ordinary semi-infinite power is identified with symmetric functions. Here it is convenient for me to take like inverse wise. This is because like I use the vectors, the powers increase when I go right in the semi-infinite world. Okay, so the infinite is actually just usual Fock space. So I will use notation AK for Heisenberg algebra, just ordinary. Take Fock module, Fock space, maybe better to say, not to confuse this Fock module for toroidal G1. Just for Fock space for Heisenberg algebra, and this standard identification of this Fock and symmetric functions, namely a negative k correspond to, okay, in my case, I put negative Newton sums, and AK is derivation by this Newton sum. Okay, this is all very standard, but is there any questions? Please ask. Okay, and the proposition The proposition, I will not comment it, but I would say that this is an exercise on symmetric functions, actually. But one can prove it in different way. Okay, that there is limit of this psi z and phi star z, and the limit is given by these exponents. So the first formula is just usual fermion. Psi z is just a fermion. Actually, I didn't say it before, but maybe I can say it here, that these wedges actually antisymmetric on K1, Kn. Therefore, this is like, so there's no V, they're literally antisymmetric. If you commute, then sign appear. So this V-wedge construction, it is not trivial, since when you write a vector as an element of, like, when you write it as a V antisymmetric tensor, then V appears. But when you just use wedge notation, nothing actually, you may not note V deformation, since it's just antisymmetric, and therefore it's not a surprise that psi is just a usual fermion. But phi star, as I said, phi star is defined in terms of subspace in tensor product. The when you like V antisymmetric tensor, and here appear V, but in very simple, the deformation happens in very simple way. Just here appears V to K. Yeah. Above we had formula psi qz phi z. Let me copy it here. Psi qz phi star z. And this gives now I should just multiply these exponents. Normal ordering gives certain prefactor, and I will obtain the following exponents. So here I get, due to this q, I get q to k minus v to k over k. And here I get correspondingly, well, just 1 minus q to the negative k over k, right? Yeah, and this is a famous formula. It determines the Fock module. Okay, let me state it as proposition. So in the limit n goes to infinity, for the action, we obtain Fock representation. P0k goes to just Heisenberg with certain coefficients, and EZ, FZ goes to this normally ordered exponents with some coefficients. And the formulas are standard formulas which determine Fock module of quantum toroidal GL1. Any questions so far?
Could you explain once again how this V disappears in this wedge product?
It's not really disappears. It's just like, well, it's what I said is just that these wedges are antisymmetric. You see, kernel of okay, maybe I can. It's a calculation. I'm not going to write it, maybe, but just like kernel of this S minus consist of functions. Oh no, I used Y notation. So it consists of functions which are symmetric such that, okay, if you like symmetric at least in two variables, like the other variables. So this is just an exercise on this antisymmetrizer. So the operator, the image of the operator depends on V. The image of this S minus is this V antisymmetric polynomials, and it depends on V, but in not very non-trivial way. It's just like symmetric polynomial. Symmetric polynomials times times this V Vandermonde, and kernel. Okay, maybe it's better to write it just like this. Oh no. Yeah, the kernel are polynomials which are symmetric at least in two variables. Any other questions?
So when you're saying that the Fock space is isomorphic to the semi-infinite exterior product, you mean we need to multiply by this Vandermonde, somehow Vandermonde of infinite amount of variables? Yes.
Well, maybe you can say it like in different ways. Maybe one way to say it is that, okay, also comment, maybe it would be clearer, that we've got commutative algebra BK of sums and the algebra gives action of Heisenberg in the limit n to infinity. So you can take this sum BKs, this Newton sums, and in the limit this action gives Heisenberg, and it's an exercise on semi-infinite powers to check that this is indeed a Fock space. So like you've got a cyclic vector, and by action of BK with positive k, any vector is mapped to the vacuum. Any other questions? Actually, this is an important point, and I would be happy to any questions. Andrei, maybe another way to say, I don't know, maybe infinite Vandermonde is a bad object, but you can look just at the symmetric function. So for each n, there's like Vandermonde times this symmetric function. Maybe you should normalize Vandermonde to be very precise, and then this symmetric polynomial actually stabilizes, and therefore you obtain symmetric functions. This is another way to say it.
Okay.
Okay, if there are no questions, let me proceed.
Maybe I have a question but suggestion. So can you move to the plan and send it where we are and where are we
Okay.
going?
Sure.
Because it's
Yeah.
already more than an hour.
So therefore, don't look at the fourth part. It's maybe very brief. So we've got 1, 2, and we finished 1 and 2. Now the only real part which remains is 3, semi-infinite construction of twisted Fock module. Okay. So consider the space Cn y plus minus 1. So now it's a vector space Cn. Okay, so excuse me, like I want to use basis E0, En minus 1 in this Cn. Then this Cn y plus minus 1 has basis yj Ea for a 0 n minus 1. And I want to use notation like Andrei Grekov said it more or less clear. So here I write it explicitly. I write E and j plus a. Now the index is any integer. And like here you see some sort of Euclidean division by n. Okay. So this is the space. And this our
so it is correct maybe to comment that twisted construction generalization of untwisted construction. So if we put n equal 1 everywhere and small, then we get formula which we already saw today.
Yeah, I'm gonna now generalize Чередник basic representation. So Чередник basic representation, we had like cy to power n, which were from like equivalently we had Laurent polynomials in n variables, and now we have this. On this space, yi acts by just multiplication. Ti acts by this formula, and now here I put R matrix. R matrix for finite GLN. So it's just this R matrix. It actually acts on just Cn tensor Cn. It's just this R matrix, not affine. Yeah. So this formula actually very similar to formula for Ti in Чередник representation, but here we had multiplication by V, and now we put R matrix here. The second term,
Roma,
yeah.
Is it some specific R matrix? Or...
It is R matrix for GLN. Yeah, it's yeah, maybe I'm cheating a bit. So it's like okay, if you asked, I will answer. So this R matrix is just, I can write it in terms of matrix units. So permutation plus V minus V inverse sum A smaller than B, E, A, tensor E. Wait, is it right? Misha, is this correct? Yeah, I believe so.
I believe not, but
What's
I
wrong?
think this
Oh,
should
yes.
be two different terms.
A not equals B.
Yeah. And should be diagonal terms, A times
Ah.
times A.
Oh, yeah, you're absolutely right. Is it correct now? I hope so.
There should be plus, yeah?
Where? Ah, yeah, certainly.
Thanks.
Welcome. Okay. So this is the R matrix. And also this action of pi, it makes cyclic permutation, and the last vector E, the index is shifted by minus n prime. So the obtained representation depends on n and n prime, right? In n, it depends on very essential way, since like the space depends on n. In prime, it depends mildly only here. I put in prime. Yeah, and the theorem says that the obtained representation is isomorphic to twisted чередник representation. As I said earlier, sigma belongs to central extension of SL2, and under the standard projection, it projects to this matrix. And well, I didn't say it before, like twisted representation means that we like take чередник representation, take the same vector space, but take new action. To act by the new action, we first apply sigma and then act.
And nothing depends on m and m prime?
Yeah.
No depend.
And yeah, nothing actually depends on, it also depends on the representative in SL2Z. It does not depend on, like, here was some kernel, is SL2Z too? Yeah. Okay, so that's the generalization of чередник basic representation. Actually, the action, so if you take not whole Dhaka, but just affine Hecke algebra, then this action was known for a long time. Namely, it appeared in the context of quantum affine Schur-Weyl duality. This Cn y plus minus can be thought of as evaluation representations of quantum affine algebra. And this tensor product is tensor product of evaluation representations. Here, important that like some people in the audience like to consider evaluation representations with evaluation parameter being a number. And here y is not a number, it's a formal variable, because here there is some operator which which does not commute with y's. Oh, I didn't say it. Okay, maybe I can say it now, that this SIY, it's permutation of yi and yi plus 1, and it does nothing with, like, oh, how to say, okay, if I've got like vector this one and all AI are in the alcove, then this SIY does nothing. So maybe it's better to look here. So here I've got y and e, and this SIY, it immutes y's and does nothing with e. Okay. So what I wanted to say is that this action of quantum affine Hecke algebra appears in this Schur-Weil duality, namely action of hy and quantum affine actually commute. Hence, we can apply antisymmetrizer to the space and obtain action of quantum affine on the exterior power. This was studied in works of Kashevara, Miller, Stern, and Leclerc-Thibon. They considered these spaces and the limit n to infinity, and they proved that the limit n to infinity is integrable level 1 module of quantum affine GLN, also known as Fock module of quantum affine GLN, but there are too many Fock modules in this talk. Okay. We are going to do similar thing for quantum toroidal. It still subjects to spherical Dhaka. Spherical Dhaka acts on the exterior power. Now this exterior power is more trickier than what we had in n=1 case. For example, it is not antisymmetric anymore. It is certain V-deformed fermionions. Okay, and consider, but still we can define vertex operators. Now I will define all of them. There are 4 of them. For any vector W. Oh no, what did I write? I'm sorry. What I meant to write is E. Now I use this E basis. Yeah, and we define operators phi k and psi k, which are wedges on the left and on the right. Oh my. And because these fermionions are really V-deformed, the operators phi and psi are really different. Also, we define phi star and psi star. Phi star takes, oh no, all the formulas are wrong. Okay, so phi star takes EJ on the left and psi star takes ej on the right. Okay, and proposition says that we still can express P1b and P negative 1b via these vertex operators, just looking at this formula for pi. Yeah. Yeah, now we have this n prime in this formula. And then we take limit n to infinity. Actually, this is very technical. This accurate description of the limit take like the most part of the paper, I guess, or significant part of the paper at least. Anyway, I will not go to details now. So we get the limit and we obtain explicit construction of twisted Fock module. This P1b, P negative 1b are expressed via vertex operators. I put hat here since like to emphasize that this like this were for infinite vertex operators in finite case, and here I pass to the limit, but the formulas look the same, though the coefficients are actually different. Let's not go to this. Here I put this capital B. Capital B is the Heisenberg. It's the diagonal Heisenberg in the GLN. So like GLN, here are on one hand this Heisenberg generated by B, on the other hand SLN. Yeah. Well, this is the main statement.
And why, how would you explain that psi and phi are intertwiners for this quantum affine algebra? Is it clear? I mean, it's not very.
Yes, it's actually it requires an argument because this semi-infinite limit is not so harmless, but like, and basically it is like intuitively it's clear. You see these operators phi. Okay, to answer Andrei's question first, I must say what Andrei means. Well, because Andrei heard some my other talks. Okay, so this operators psi hat can be, so we can consider it's a comment. It's a comment to the theorem that I can consider operators phi, psi, phi star without index. These are the following operators which are intertwiners. So they intertwine the actions. Actually, the definition makes sense for any pair of representations of quantum affine, but they do not always exist. Right, or maybe not unique up to a scale. Okay, so there are four, like you can consider tensor product with Fi with evaluation representation on the right, or on the left or on the right, or you can map to space tensor by evaluation representation on the left or on the right. Therefore, we've got four operators, and the operators used above are components of these operators. So if I apply phi hat to tensor product, then it is phi hat with index k applied to the vector. Right. Well, Andrei, now I'm ready to answer your question. You see, you can check intertwiner property for the operators, and it is actually easy. It is obvious. And then you just take the limit n to infinity.
So it's an exercise, right?
Uh,
No, I mean, to check that the intertwining property is obvious, right?
no, yes. If it's not obvious, then it's like, I mean, for infinite case, this is really like you just have to recall all the definitions, and then this is obvious. But the limit is a bit tricky. Should I use? Sorry for the tautology, but I used a trick. So when I proved it, it wasn't obvious. Okay.
Are there any other questions?
Yeah.
Shall we just thank the speaker?
No, wait, you mean Gorsky-Negut conjecture?
Maybe already people are tired.
Yeah, no, people are tired unless you can just say in one sentence.
Actually, I may okay, maybe in 2 sentences. Sorry,
before Gorsky-Negut conjecture, did understood right that you gave 2 definitions of this module? Yes, one definition is via generators, via this y's, yes, y generators and Dhaka-like operators, yes. And another definition is what?
Another.
Yeah, this is one definition, and
like maybe on one hand, okay, let me say it. It's actually a very good point. So on one hand, this is a twisted Fock module. On the other hand, the action is obtained from this semi-infinite VVH. Which is integrable level 1 module of quantum affine. So we've got quantum affine. It acts here. And we've got toroidal Gil1, and it acts here. So as Misha said in the beginning of the talk, this is some sort of duality in the sense that there are 2 algebras acting on the same space. Yeah.
It does mean that one of them is subalgebra, and other no. I mean, they can be constructed from the same or maybe related things, but they're different. Like Schur-Weil duality.
And you didn't give a definition of generators of this GON, yes? Or I missed? the definition?
I just like you see, this was tensor product of evaluation representations for quantum affine.
Mhm.
Then
Okay.
it acts on the exterior power, and we can take the limit.
Mhm.
So, so this actually gives action in the basis.
Mhm. And,
There is some trick, some technical details about the limit, as Roma mentioned, but morally, it's clear. We have each space is representation. We take tensor products and this quantum group, ordinary quantum group coproduct, not neutrino, just standard coproduct.
and where is the second quantization parameter here?
Oh, yeah, that's also a very good question. Here it's here. Maybe it's not. Maybe I can go to n=1 case. So this is also a very good point. Thank you for this question, Kolya. There were two operators, and they do not depend on Q. They depend only on V. Actually, the first operator does not depend on anything, and the second depends on V. And Q appears here as a shift.
Mhm.
So in this formula, Q also appears actually as a shift.
Yeah,
So,
but this is toroidal part of the correspondent. Yes. This is
Yeah.
the definition of toroidal generators.
yes.
And where is second quantization parameter on affine part? On not
There's
toroidal.
no this parameter. It's just UV gel n hat, like V equals Q2.
And action of these two algebras commute, and one
No,
action.
no.
Okay. And what is the
No.
statement? So.
No, it's completely
Yeah.
impossible.
Sorry. Yeah. Sorry.
The
Yeah.
representation. This is the irreducible representation of.
Yeah. They both act on the same space, not.
Yes. They all both act on the same space, and the representation is reducible. If you want, like what these algebras have in common is Heisenberg. So Heisenberg for GLN is Heisenberg for quantum toroidal GLN.
And to say more about relation among these two algebras, you have to say what is Negut-Gorsky conjecture. Yes.
Well,
No?
it's one of statements, but like I'm not sure that this is like. In a sense, yes. In a sense.
Okay, thank you.
Okay. So I think we should thank Roma for the talk, Misha for the comments, thank everyone who survived till this time. So maybe the most simple question today, Roma, what time is your defense?
4 p.m.
So everyone who wants to continue discussion are welcome on Thursday to Roma's defense. Спасибо всем, наверное. Игорь, ты живой еще? О, какие кремни остались. Ладно, тогда, Паш, выключайте, да, там.
Ну ладно, спасибо, пока.
Спасибо.
Не можете, да? Тогда я сейчас позвоню Игорю Моисеевичу, прошу вас выключить. Ладно, спасибо.
Да.
Sure.